cool. I'm a mathematician, and maths is boring, right? Maths is boring. I know this. I sit in a room all day and I think about it. And people often say to me, like, what do you do all day? And like, that's the truth. I sit in a room largely by myself, and I think about things. Sometimes I write them down. The things that I think about are how to model blood flow in the human heart with maths. It's like kind of a big deal because like you have a heart, it's important to your continued existence. We care about this. And I do this using a set of equations called the Navier-Stokes Equations. And they basically just describe how a fluid moves. Any fluid, air, water, your beverages, blood. So these are made up of several terms. The first I want to tell you about is this one in red over here, this like wonky looking V. It's new, it's viscosity. Viscosity is basically just a measure of how sticky stuff is. The next term that I want to tell you about is rho, this like quotient here. It's the density. The density is kind of like mass, it's mass per unit volume. So you know that thing where like a kilogram of steel weighs exactly the same as a kilogram of feathers, but you've got more feathers, 200 times as many feathers, or 200 times as big a volume of feathers as you have of steel, because steel is 200 times as dense as feathers. So you've got the same mass, but a different density. It's mass per unit volume. It's straightforward, right? But we also want to model movement. Like, if your blood's not moving, you're dead. You shouldn't be dead. That's not a good thing to be. So if something's moving, it has to be changing in time, which is what this thing over here on the right-hand side does. It just says something is changing in time. And if something's moving, it has to have a velocity, which is this beautiful term, u, highlighted in red, everywhere, as we can see. And if you've got a flow, if you've got a velocity, you have to have a flow. It's like the amount of stuff that's going places. And if you've got a flow in a container, it's got to be exerting a pressure, which is P here on the container. And that's basically what I think about all day is how does the pressure in your blood vessels relate to the flow in your blood vessels. So the first thing that we want to talk about is vessel size, because you have like vast orders of magnitude difference between the sizes of blood vessels you have in your body. So all of the tables should have a little polythene baggie in the middle. They're full of straws. Can y'all please get 3 straws? You should have a short, skinny one, a long, skinny one, and a long, fat one. Can y'all get straws? Straws. There should be the perfect number of straws. When you have your straws, stick the short, skinny one and the long, skinny one in your mouth, walrus style. The other end can like either be in the air or in your beverage. I don't particularly care. You do you, but walrus style as such. Like little tusks. And when you've done that, I would like you to suck through them. And hopefully, what you should feel is that the flow through the short one is bigger than the flow through the long one. Hopefully. If I haven't done this properly, then I like lose my mathematical chops. I have to give my degree back. It's very embarrassing. Could you please swap out your short, skinny straw for the long, fat one, and do the same thing? You should, again, feel that the flow through the long, fat one is bigger than the flow through the long, skinny one. This is basically because of the amount of stuff that is near the outside wall of the tube, which is very, very important for me to consider when modeling blood flow, because the biggest artery in your body is your aorta, and it has a diameter of about 2 centimeters, i.e. the same as a hose pipe. The smallest blood vessels in your body have a diameter of about 50 micrometers. That's like 10,000 times different. 50 micrometers is the average size of a human hair, by the way. It's pretty small compared to a hose pipe. They also vastly vary in length, between about 3 centimeters, again, your aorta, and like a couple of millimeters, your capillaries. This is one of the primary things that I think about. I have lost my clicker. There it is. Oh, we also have gravity. We're going to come back to that in a little bit. Frequency. So you have a heartbeat. Mine is currently 111 beats a minute. Fun side note, that's like 1 every half second. That's a bit high. If you go to your doctor with like resting heart rate of 111, you're probably going to die quite soon. Again, we want to avoid death. Death is bad. So in order to deal with this frequency thing, I use a thing called a Fourier decomposition, and I can like reasonably liken your entire lifespan to a melody. So, or like just a series of heartbeats, like maybe 6 or so, to a melody in which each heartbeat is, can we hear that? It's kind of like a chord. So I can play that, which is C major, if anyone cares. In this chord, we have 3 notes, which are C, E, and G. Yes, G, good. Can't remember keys. So what I do is I look at each heartbeat individually, and then I say to myself, but what is happening within this heartbeat? And then I say, there are these things happening, which is kind of like the notes. Like, it's much easier to learn a piece on the piano hand by hand and then put it all together, or it's much easier to learn how to play a chord than it is to just like go and sight read the entire thing. Like, it's difficult, and so is maths. And basically what I do is I use this Fourier decomposition, and then I get a whole bunch of answers, and then I just add them up at the end. And it's so easy, it's so nice, it's super duper elegant. And I get to compare your life to a song, which is always nice. We also have gravity, and can I get a like willing victim, a helpful volunteer? Here is a platypus that I stole from my mother. Here is a platypus that I stole from my brother. Neither of them are happy with me. Cool. So basically, the point is, when I have a working mathematical model of anything, I want to check that it's true, that it's right, that it does what I want it to. And we do this by comparing my results to the data found in the literature. Because I'm a mathematician, I don't go and get my own data. That's daft. Blood kind of skews me out. Like in person, I tend to faint. But your blood pressure depends on whether you're standing up or lying down, and people in the literature don't often specify whether people were standing up or lying down when their blood pressure was measured. So, as a demonstration of this, and to convince you that I'm not lying, if you could squirt into your bucket from a great height. Yeah. So this small distance is giving us a very small flow, but this much bigger distance is giving us a very big flow. We can stop now. I think you've got the point, right? You are convinced that I'm not just lying to you about gravity. It's about the distance over which gravity is acting. So if you're lying down, you've got a very small distance, because I'm a skinny person, but I'm also reasonably short, but I'm much taller than I am deep. There's more of me for gravity to act over, so gravity has a much bigger impact on my blood pressure when I'm standing up. Also, fun side note, giraffes have a series of valves in their neck, so when they stand up, they don't get immediately lightheaded and fall over. Humans don't have those. Giraffes are superior to humans in at least one way. The very last thing that I want to tell you about is non-Newtonian fluids, and can I get another different willing victim, please? Someone? Anyone? You get to play with corn, flour? Wonderful! I always enjoy people. So, I mentioned earlier, do you want to give that play while I say words? The minimum radius of any blood vessel in your body is 50 microns, that of a capillary. That's because that's the skinniest tube that a red blood cell can fit down, and at such small scales, blood is thoroughly non-Newtonian. Like this stuff, by non-Newtonian, I just mean that it doesn't behave like water. So if you you can pour it, you can slosh it, it like does things. Yeah, it's like nice and liquidy when you're gentle with it. But then when you stir it, you can like pick bits up and it cracks and it's wild. It does that. It's cool. So I'm not saying that blood behaves in that way. Thank you. You can go sit down. No one knows how blood behaves on such a small scale, but I'm mildly curious about that, and it's important to modeling blood flow. I don't really have a point about all of this. It's mostly that my job is hard. It's interesting, and I thought you'd like to know. Thank you for listening.